Okay. What was I saying? I'm forgetting many things. Okay, so both the graphs are different. Okay, as per their x-axis and y-axis. So on the x-axis of the bottom graph, you have the upper speed of the speed group, and the y-axis you have the cumulative frequency. If I go to this table, the second column on the x-axis, and this column, I think there's a sixth column, cumulative frequency on the y-axis. Okay. Now you can see the first graph starts at 0, ends at 0. Okay, why? Because if you look at the speed groups which we have made, I have a 0 value group at the start and a 0 value group at the end. Okay, so here I will explain one point which I did not explain yesterday, which is about making extra groups at the start and at the end to close the graph. We want a closed shape graph for the frequency distribution curve. Why? I'll come back to it tomorrow, inshallah. But we need a closed shape graph for the frequency distribution curve. So what happened actually in the field? My minimum speed, the actual minimum speed of the vehicles was not 30. It was somewhere above 32. It was somewhere above 32. Okay. So I made an extra group from 30 to 32, knowing that I will have 0 values in that, because the actual lower limit of the speed was not 30. It was above 32. So I made an extra group knowingly that I will have a 0 value in it. Similarly, the highest speed was 66 miles per hour. 66 miles per hour. And again, I made an extra group, even though I knew that in that group there will be 0 values. Okay. And why did I do it? Because when I plot them, I will have 0% frequency for the first group, 0% frequency for the last group, and when you plot it, you will get a closed shape of the curve. Closed shape meaning what? It will start from 0 and end at 0. Start from 0 and at 0. Okay. If you come to the second graph, again going to the same the groups, because of the extra 2 groups I have made, the first value will always be 0, because the first group has 0 frequency. The last value will always be 100, because cumulative percentage can maximum go to 100. It will not go above 100. So even for the second graph, I know the first value and the last value, 0 and 100 respectively. Now you see the first graph. On the second graph, it's not so obvious, but in the first graph, the top one thing is very obvious here. The curve which you see here is not plotted by joining all the points. The curve which you see in the frequency distribution graph is not plotted by joining all the points. Okay, so the curve which you see here is what we call as best fit curve or best fit line. A best fit curve or a best fit line. What is the best fit curve? This is a curve which passes close to majority of the points in your data set. It passes close to or over majority of the points in your data set. Okay, but it does not join each point one by one. It does not join each point one by one. Okay. Now, why are we making the best fit curve? Why not just join all the points? Because if you see, if I try to join all the points, you will never get a meaningful shape of the curve. If you join all the points, you will never get a meaningful shape of the curve. Then the remaining calculations, what we are about to do, will become much more complicated. So this curve which you see here is a parabolic curve. Okay, but if I join all the points, you will never get a parabola or a crash curve or a sag curve. You will never get that. Okay, so the remaining calculations will become difficult. So we try to plot a best fit curve, or we try to make a best fit curve so that we have a meaningful shape. And for that meaningful shape, we know the properties, we have the equations from geometry and so on and so forth. So we plot the best fit curve. How to plot the best fit curve? Okay, there are some methods, mathematical methods as well. I will not go in that detail. If you have covered it in probability and statistics, very good. If you did not cover it, I will not bother to go into it. But there's a method in Excel. If you plot a chart in Excel, then you can make a best fit curve in Excel. Okay, and the option is known as plotting a trend line. So any of you who has plotted a curve in Excel, if you right click on the curve, it will show you the option to plot the trend line. So trend line is basically the best fit curve or the best fit line. And why do we need the best fit line? So that the remaining calculations can be done using a meaningful, like a known geometric figure. Okay. So for the second curve, they must have done the same thing, but points are so close to the line, we cannot see whether it's a best fit curve or it's actually a curve which is plotted using point-to-point joining. But this is what you actually do. Okay, joining each point to the other point is not the objective here. Objective here is to get a meaningful known geometric figure. Okay. After plotting the curve, now you can start with the calculations or start with the finding out the statistics of the data. So the most common descriptive statistics of spot speed data are of two types. Descriptive statistics means what? Statistics or numbers which are used to describe the data, the nature of the data. Okay, statistics which are used to describe the nature of the data. We call them descriptive statistics, and they are of two types: central tendency and dispersion. Descriptive statistics are of two types: central tendency and dispersion. Central tendency means what? The measures or statistics which represent the central values of the data, the middle values of the data. So statistics like mean, mode, median. Okay, these are statistics of central tendency. Okay, I think you know most of them. Then we have statistics of dispersion. Dispersion from where? Dispersion from the central values. Dispersion from the center portion of the data. So first of all, you must calculate central tendency statistics so that you can calculate the statistics of dispersion. So dispersion meaning the spread or the variation of data from its central value or from its central portion. So statistics of dispersion are those statistics which define the spread or variation of the data from its central value or central portion of the data set. Okay, and start with the calculation of measures of central tendency. The most obvious one, the most commonly used measure of central tendency is mean. Now I've explained this point yesterday as well. So when we calculate the mean of spot speed, what type of mean speed is it called? When you calculate the mean of spot speed, what type of mean speed is it called? So we discussed two types of mean speeds earlier in the previous chapters. So when you are taking the mean of spot speed, what type of mean speed is it? Time mean speed. Yes, Haya, very good. Yes, time mean speed. Raneem, right? So time mean speed. Okay, and again a note for frequency distribution data, calculating the mean is not just by summing up all the values and divide by the total number. Okay, so it's different, which you can see in the equation here of x bar. X bar is the mean speed. Okay. Now, why do I need to make it complicated? Why am I making your lives complicated if I don't want to, give you F? Okay, why I'm doing this? Now, the reason for this, if you look at the table here, the frequency distribution table, the first three columns represent the speeds, right? The first three columns contain the speed values. Okay. Now, if you take the average of any of these three columns, simple average, summation of all the values divided by a total number. If you take the simple average of any of these three columns, you will always get a constant value. And that value is not dependent upon the speed of the drivers on the road. Because remember, you made the speed groups. Okay, you had the range and you decided that I will make the speed group of 2 mile per hour interval, and the middle speed will be this much, and so on and so forth. So you are actually deciding these values. The first three columns do not have anything to do with the values of the speed which you have observed in the field. Okay, so taking the simple average of any speed column will not give you the accurate mean speed of the drivers. Okay, so what we have done, we have come up with a method in which we are using the frequency in each group, and we are also using the middle speed of the group. Okay, so first of all, you calculate the product of number of values observed in that group, and you multiply it with the middle speed of the group, which is n into s, this column. Okay, so you calculate this column. So what will happen if a group has more values? If a group has more values, then this factor will be higher for that group, right? This factor will be higher for that group. So the mean speed will be closer to that group. The group of speed which has higher observations, the mean would be closer to that group because this factor n into s will be higher. Okay, so clarification: mean for frequency distribution data doesn't mean taking total number of summing all the values dividing by total number. Okay, it will be wrong because the speed groups are made by the observer. It has nothing to do with the observations in the field. So we do n into s, so that number of observations are multiplied with this speed. Okay, and then you do the summation. Okay, summation is also given at the end here. Okay, so this is summation of n into s, and this will be divided by the total number of vehicles you observed. The total number of vehicles you observed, n value. Again, a common mistake which has been done by other students previously, they take the total number of speed groups. They just count these values. How many rows are there? This is also wrong. Okay, divide by number of values you observed, not number of groups you made. Okay, so how many values you observed? 368. You have observed speed for 368 vehicles. Okay, so n into s divide by 368. Okay, so summation of n into s is this much, divide by 368. Give me the mean speed. Let me go there. Open the notebook so that you have the values. Okay, mean 17736 divided by 36. How much is it? 48.2. 48.2 miles per hour. Okay. Okay, good. 48.2 miles per hour. This is how you calculate the mean. Okay. The next measure of central tendency is median. Okay, and you already gave me an answer for median yesterday. So this is the middle value, right? This is the middle value. So where is the middle value? Middle value means that 50% of the observations were above this value and 50% of the observations were below that value. Okay. Go to the cumulative frequency distribution graph. This is the graph which will tell you about the median. There is a graph which will tell you about the median. So if you want to find out the median, so median means middle value. Middle value means 50% value. The value which is dividing the data into 50% halves, 50-50 halves. Okay, so locate 50% on the y-axis. Okay, drop a perpendicular towards the curve. Okay, and the point where this perpendicular will intersect the curve, from this point you will drop a perpendicular towards the x-axis, and this value on the x-axis will be your median. Okay, so this is, I think, again close to 47 point something. I will show you in the next slide the exact value. So this is 47 point something. So 50% of the drivers are driving below this value and 50% of drivers are driving above this value. How do I know that? Because the cumulative frequency at this value is 50%. Okay, the cumulative frequency, the cumulative percentage of drivers up to this value is 50%. Okay, so obviously 50% are below it, 50% are above it. Okay, so median will be found from the cumulative frequency distribution graph by locating 50% on the y-axis, dropping the perpendicular on the curve, and then finding out the value at the intersection point on the x-axis. This will be the median. Okay, then some other parameters. Now you can see the median is mentioned here, okay, which is where is it? 47.7. Okay, so this is the median. Okay, now the mode. Another measure of central tendency is the mode. How do we define mode? Which of you can define mode for me? What is the mode? If I give you a data set and I ask you what will be the mode of this data set, what would you do? The most occurring number, most repeated value, right? Okay. Now this is again true. This definition is true in general sense if I give you individual values. But if the values are frequency distribution, are sorted out in frequency distribution, then you don't have repeated values, right? You don't have any values. You just have frequencies. Okay, you just have frequencies. If the data is sorted into frequency distribution, then you don't have the individual values. You just have frequencies for each group. Okay, so the mode will be the value having the highest frequency. The value having the highest frequency. Okay, so the frequencies are plotted on this curve, the top curve, frequency distribution curve. So on this curve, locate the highest point of the curve, which is this one. Okay, from this point, drop a perpendicular on the x-axis, and the point where the perpendicular meets the x-axis will be the mode. Okay, so locate the point, the highest point on the frequency distribution curve. From that point, drop a perpendicular on the x-axis, and wherever the perpendicular meets the x-axis, that value is your mode. That value has the highest frequency. Again, a common mistake is students locate the highest frequency point and then find the value of mode from the y-axis. Mode is a speed. Okay, the speed which has the highest frequency. So I am interested in finding out the speed which has the highest frequency. Okay, so the speeds are given on the x-axis. Okay, so find for the highest point, find out the value from the x-axis, not the y-axis. Y-axis is the frequency. Okay, so if you give me the value from the y-axis, you are telling me the frequency of the mode. You are not telling me mode. Mode is on the x-axis, the value of speed which has the highest frequency. Okay, the value itself, not the frequency of that value. Okay, so mode will be from the x-axis. Okay. Then another measure of central tendency, which I explained yesterday as well, that is the pace. The pace. To refresh your minds, what is pace? It's a 10 mile per hour range of speed in which the proportion of drivers is more than any other range outside that value. Okay. Pace is a 10 miles per hour range in which the proportion of driver is more than any other range of that data. Now, how do I find out the pace? Okay, now the method is graphical, so pay attention. Okay, I don't know any mathematical way to find out the pace. I have never seen it in any book. Okay, so you need to pay attention because there will be no equations. Okay, if you are relying on I will sleep now and I will later on see the equations, there are no equations. Pay attention here. First of all, take a ruler or a piece of paper or a cardboard, any object, and the width of that object should be equal to 10 mile per hour on the x-axis of this graph. I'm talking about the top graph, percentage frequency graph. Okay, so take a piece of paper or a ruler or cardboard, whatever object, and the width of that object should be equal to 10 miles per hour on the x-axis of this graph. Okay, so you put this object on the graph, on this graph, and then you slide it. Slide it towards the middle of the curve. Slide it towards the middle of the curve. So the higher values, you can see the higher values of the frequency are towards the middle of the graph, right? They are not exactly in the middle. Okay, they are not exactly in the middle as well. Okay, keep this in mind as well. So you cannot say that it will always be in the middle. No, it can be slightly forward or backward from the exact middle of the curve. Okay, so that's why we have the graphical method. Okay, so then you slide this paper or cardboard towards the middle of the curve, and you will stop where? You will stop when one edge of that object is on one side of the highest point and the other edge is on the other side of the highest point. So this is your highest point, right? So I have slided this object. This was my object. Okay, it was a cardboard or a paper or a ruler, whatever. The important thing is that the width of this object was equal to 10 miles per hour on the x-axis. Okay, so I slide it, and when I reach this point, when I reach this position, I'll stop here. What is this position? Now you can see that one edge of the object is on one side of the highest point, the other edge of the object is on the other side of the highest point, and at these 2 points find out the values on the x-axis. So this value and this one, and these 2 values are the range of pace. These 2 values are the range of pace. So this value is 42.5 and this value is 52.5. Okay, so the percentage of drivers who are driving between 42.5 and 52.5 are more than any other range outside these values. So if you take a range which is below 42.5, or if you take a range which is above 52.5, the proportion of drivers in those ranges will be less than the proportion which you will find between 42.5 and 52.5. Okay, the highest proportion of drivers are driving between 42.5 and 52.5. Any other range taken in this data will give you a lower proportion. Okay, so these are the values for the pace. Again, a small clarification, these are the values of the pace. Till now, I have not calculated what is the exact proportion of drivers driving in this range. Are they 50%, 60%, 70%? Till now, I have not calculated it. I am just telling you whatever that proportion is, it is between 42.5 and 52.5. Now I'll stop here for a couple of seconds. Any questions? I know the procedure of PACE can be difficult. Any questions regarding PACE or anything which I've discussed earlier? Any questions? Is it clear?
Sir, how can I determine the size of the roller or the object?
Yeah, it should be. So you have already plotted the curve. Okay, so the curve is in front of you. So when you plotted the curve, you must have selected a scale, right? So according to your scale, for example, 2 inches was equal to 10 miles per hour on the x-axis. So the size of the roller should be 2 inches. Okay, you cut the roller or the paper so that its width is 2 inches. Got it? Any other question? Any other query? Okay, thank you. So this is these are the measures of center tendency: mean, median, mode, and pace. Okay, now we will move on to measures of dispersion. Measures of dispersion. So the first measure we will discuss is standard deviation. Standard deviation. I already explained what does standard deviation mean. So who can remind me the definition of standard deviation? What is standard deviation? Tell me. What do you remember is standard deviation? Go ahead. Standard deviation means what? How do we define standard deviation? I mentioned it yesterday and today as well. Standard deviation. How do we define it? Nobody remembers? You cannot remember what we did yesterday. What will happen in the exam? Then you will be asking me for more time because you need to time travel, right? You need to time travel, go back to the previous weeks and see. Anyways, so
can
yeah.
you repeat the question, please?
What is the standard deviation?
Standard deviation is the average of the distance between the average values and the values itself. So the difference between the values and the average, this is the standard deviation.
Yeah, good. You were Googling it?
No. No, I know it from static case. course.
Okay, good, yeah. So many things which you are seeing here are already covered in statistics. But anyways, you don't remember what we did yesterday. How can I expect you to remember what you did in statistics? Anyways, standard deviation, average difference between the mean and the other values. Now you see 3 equations here on the slide. The first equation, this one, is used for calculating a standard deviation if individual values are given. Normal values like you have. For one car, I have one value. Okay, for each car, I have a value and give you 10 values, 20 values, 15 values, and you are calculating the standard deviation for those values. Okay, discrete individual values which are not merged into frequency distribution or speed groups. Then standard deviation can be calculated using this equation. This is a standard equation for standard deviation for normal data set. Okay, a normal data set where each value is individual value. But if you have frequency distribution data set, then we need to again incorporate the speed groups and their frequencies in the equation of standard deviation. So this is why you see the second equation here. So this is the main equation, the raw equation for calculating the standard deviation of frequency distribution data. Okay, this is the equation for calculating standard deviation for frequency distribution data. Okay, so small n, number of values in each group, capital S, middle speed of the group, x bar, mean of the data set, mean speed of the data set, which we already calculated, okay, just a few minutes ago, and capital N, total number of values in the data set. Now keep in mind, small n and capital S, every group has a different value for them. Number of values in each group and the middle speed of the group is different for each group. X bar is for the whole data set. So for one data set, X bar will be constant. Same thing with capital N as well. Capital N cannot change from one group to another group. This is the total number of values. Okay. One more thing, capital S, you can see I'm using capital S here and I'm using a small s here as well. Capital S means middle speed. We have already used it. A small s means standard deviation. Capital S, middle speed, small s, standard deviation. Okay. Now, if you open the bracket and multiply n with both the entities here in the bracket, you can simplify the equation into this form. Okay. So summation of n into s square as it is. Okay. And then you do summation of n into x bar square. Okay. So x bar square is a constant. So summation of n will give you capital N, right? Capital N equals summation of n, summation of all the values, total. Okay, capital N is total, summation of n, small n. Okay, so this is a simplified form of the raw equation for standard deviation. Okay, so obviously we will use a simplified form, this one. Okay, but this is from where it is coming. Now we have already calculated all these values. Summation of n into s square already calculated, given in the table, the last column, and summation is also done here. Okay, and we know capital N 368. X bar is the mean speed. We just calculated it at the start of the lecture. So let us calculate standard deviation. Again, I will use small s here. So square root summation of n to s minus capital N, which is 368, multiplied by x bar square. So x bar is the mean, 48.2. Let me use a bigger bracket here. Divided by n minus 1. N is 368 minus 1, 367. Okay, how much is this? Give me the value of standard deviation.
It will be Dr. 44406. 3406.
3406?
No. 44406.
No.
This is what I got.
Will be a small number.
The values.
First of all, do this within the bracket and then take the square root.
Sorry, Doctor, I had a mistake. It became 6.06.
6.06.
6. Yeah.
Okay, standard deviation units are again miles per hour. Okay, average for mean the units were miles per hour because the speed was measured in miles per hour. Okay, and for standard deviation you are taking the difference from the mean and the other values. So all values are in miles per hour. Taking the difference of miles per hour will give you in miles per hour. So the units of standard deviation are miles per hour. Okay, so there's no conversion here. Okay, I'm not doing any conversion. All units are going consistent. Okay, any questions? Any questions? Clear? Okay, moving on. Yes. Now related to pace, so I've already defined pace, right? The 10 miles per hour range, which has the majority of the values, the highest proportion of drivers. Regarding pace, there are two parameters. One is the range of pace, which I already explained earlier. For the example, it was 42.5 to 52.5. Okay. That range is considered as a measure of central tendency. The values of the pace are considered as measure of central tendency. Now, how many drivers are actually driving in that range is considered as measure of dispersion. Measure of dispersion. Okay. So I know the pace is 42.5 to 52.5. I use the ruler and I slide it on the graph and I found the values from the x-axis. Okay, so I already found it. 42.5 to 52.5. But how many drivers are driving in that range? Is it 50%, 60%, 70%? What is the exact value of percentage of drivers driving in between 42.5 and 52.5? What is that exact value? That value is a measure of dispersion, and now I'll explain how to get that percentage. Though that percentage will be taken from the cumulative frequency curve, cumulative frequency distribution curve. Okay, so first of all, find out the pace values. Then locate these pace values on the x-axis. So 42.5 is here, and 52.5 will be here, somewhere here. Okay, this is 42.5, this is 52.5. Okay, now in this case, in this slide, the graphs which are plotted in the book, the graphs are plotted one over another, and the scale for the x-axis is same for both the x-axes. The scale is the same. So instead of plotting the value from the bottom axis, they are plotting it from the top axis. It doesn't make any difference. Okay, because the scales are the same. Okay, but don't get confused. If you are plotting these graphs yourselves, then just locate the value of the upper limit of the pace range and the lower limit of the pace range and plot them from the x-axis. Okay, and then after you plot them from the x-axis, you will reach a point on the curve. Okay, these 2 points, and you find out the values of the y-axis for these 2 points. Find out the values of the y-axis for these 2 points. Now, what we have plotted on the y-axis? On the y-axis are cumulative frequency. On the y-axis, there is cumulative frequency. Cumulative means what? So, for example, for 42.5, the cumulative frequency is 16%. This value is 16%. Okay, it's written here. The exact value is written here. 16%. Now, this 16% represents what? 16% of the drivers are driving up to 42.5. Cumulative means what? I've already added all the values up to 42.5, right? This is what we mean by cumulative. So up to 42.5, what percentage of drivers are driving? 16%. Similarly, when I get the value from the y-axis for 52.5, I get 77%. Okay, so what this 77 represents? This represents that up to 77%, sorry, 77% drivers were driving up to 52.5. Okay, so 16% drivers were driving up to 42.5, so 42.5 or less, right? and 77% drivers were driving up to 52.5. So 52.5 or less. Okay. How many drivers? What percentage of drivers are driving between 42.5 and 52.5? Then I will take their difference. Okay, I will take their difference, what they have done here. Okay, difference of 77 and 16. 77% drivers up to 52.5, 16% drivers up to 42.5. So their difference will give you the percentage of drivers between 42.5 and 52.5. So in this case, it is 77 minus 16 will give you 61%, right? It will give you 61%. So 61% drivers are driving between 42.5 and 52.5. Okay, so if you take a range below 42.5 or if you take a range above 42.5, the percentage of drivers in those ranges will always be less than 61% in this data set. Okay, also whatever percentage you find for your own data set, the any other range will have lower percentage than that value. Okay, so this is how you find out the percentage of values within the PACE range, and it is a measure of dispersion. Okay, any questions? Is it clear? Clear? Should I move forward? Okay. Another important measure of dispersion is 15th and 85th percentile. 15th and 85th percentile. Now I explained the term percentile yesterday as well. Percentile means what? Percentile is the upper limit for a particular proportion of the data. Percentile is the upper limit for a particular proportion of the data. For example, if I tell you 85th percentile speed is 55 miles per hour, it means 85% of drivers were driving at 55 miles per hour or less. Okay, so percentile is the upper limit for the number which is given with the percentile. 85th percentile means this is the upper limit for 85% drivers, and the value will be the upper limit of that much percentile. Okay, so what is important about 85th or 50th? Or let me first of all let me tell you how do we get the percentile values. For calculating or getting the percentile values, we will use the same method which we have used for getting the median, for acquiring the median. If you remember, we got the median from the cumulative frequency curve, the bottom one in this case. So the median was basically the 50th value on the curve, right? The 50th value. So you located 50% on the y-axis, then you found the value on the x-axis for the curve. Okay. Similarly, 85th percentile is the 85th value on the y-axis, and 15th percentile is the 15th value on the y-axis. Okay, so cumulative frequency curve, the y-axis of the cumulative frequency curve is directly the percentiles, is directly giving you the percentiles. So median itself is the 50th percentile. Median, the middle value, is the 50th percentile. 50% drivers are up to it and 50% are above it. So median is 50th percentile, 50. So how do I get the 15th percentile? Locate 15% on the y-axis, drop a perpendicular on the curve, and find out the value on the x-axis. In this case, it is 42.4. This one. For 85th percentile, find out 85% on the y-axis, drop a perpendicular on the curve, and find out the value on the x-axis for that point. In this case, it is 54.7. So 15th percentile is 42.4 and 85th percentile is 54.7. Okay. Now, what is the significance of these values? Now, research and experience has shown that drivers who are driving below 15%, 15th percentile, and the drivers who are driving above 85th percentile, they are not normal average drivers of the road. Their speed is either too low or too slow as compared to the other drivers. Drivers who are driving below 15th percentile are too slow as compared to the normal average driver on that road. And drivers who are driving above 85th percentile are too fast for the normal average driver on the road. Now, the driver who is going too slow may have some unique reasons. For example, his car is not performing well. For example, he is busy using the phone. He is tired. Okay, so he's not normal. He's not average. Okay, same thing for the driver who's driving above 85th percentile. He's again not average normal driver. He is having some problems. Maybe he is going in a hurry to hospital. He's not feeling well. Something happened at his house, so he is in an extra hurry. Okay, so those drivers, if you want, there's a range of speed for normal drivers, normal average drivers who are driving in normal circumstances under normal conditions. They drive within the range of 15th and 85th percentile. Okay, normal or the range of speed for normal average drivers driving under normal circumstances can be taken between the range of 85th and 15th percentile. So normal drivers are driving between 54.7 and 42.5. This range can also be used for calculating an approximate value of standard deviation. So we have already calculated standard deviation using the square root equation, right? That is the actual equation. That is the one which we should prefer, and that is the one which we should always use. But sometimes the data is not available, we don't have the time, or because of any other reason, we cannot use the square root equation, the actual equation of standard deviation. Then you can use the these two values, just two values, to find out the approximate value of standard deviation. Okay, how? The equation is given here. Okay, this is the equation. Sorry, you cannot see the 2 here. Denominator is the 2. So you take the difference of the two values, 15th and 85th percentile, and divide by 2. That will give you the approximate value of standard deviation. Okay, so SEST, EST represents approximate, estimate. Okay, so 54.7 minus 4, the 15th and the 85th percentile, divided by 2. So how much is it?
6.15.
6.1. Okay, now you can see this is very close to the actual standard deviation, right? This is very close, but not the same. Very close, but not the same. So this is why, and this difference will always be there. And I told you the method which you should prefer for calculating the standard deviation is this one. Okay, this is only to be used if you have some restriction of the data, you don't have the time or something like this. Okay, so this is only used if needed. The second method is only used if needed. Okay, now standard deviation, percentage of vehicles in pace, and 85th and 15th percentile, the range of 85th and 15th percentile values. Any of these values, higher value means more dispersion. So more standard deviation means more dispersion in the data. If you have a higher percentage of drivers in the pace range, sorry, that is the other way around then. If you have a higher percentage of drivers in the pace range, that means dispersion is less. If you have higher percentage, so instead of 61, if I got 65, that means less dispersion in the data. So percentage of values in the pace range increases, then the dispersion decreases. Value of standard deviation increases, dispersion increases. More difference between the mean and the other values. And if the range of 85 and 15th percentile increases, that means again more dispersion. So higher value of standard deviation means more dispersion. Wider range of 85th and 15th percentile means higher dispersion, and higher percentage of drivers in the pace range means less dispersion. Okay, so percentage of vehicles in the pace range are inversely proportional to dispersion, but the range of 85th and 15th percentile and standard deviation is directly proportional to the dispersion. Okay, so this is it. Tomorrow, inshallah, we will discuss the concepts of normal distribution and something else. If you have any questions, any queries, anything you want to say, please go ahead. I'm ready to listen. Anything? Any questions, queries, confusion? Okay, you are welcome. So I'll see you tomorrow, inshallah. Have a nice day. Yes, you too, Ali. Have a nice day. And thanks for listening. Thanks for participating. Inshallah, see you guys tomorrow. Assalamu alaikum.